myself Dr. Vijaykumar, Associate Professor, Department of Electronics and Communication Engineering, Aditya University. In this session, we are going to solve the problems on joint moments. So, first learning outcome we will be seeing in this session is, we will define the joint moments. So, at the end of this particular session, you need to know the mathematical definition of joint moments, and also we apply the concept of joint moments for solving the practical problems. So, any practical problem is given based on the joint moment, you should be able to in a position to solve that problem. So, before going to the joint moments formula, so if you want to compute the expectation for a function, the formula is expectation of function. It is two dimensional. If it is a single dimension, expectation of g of x is equal to minus infinity to infinity g of x fx of x dx. So, for a two dimension, the formula will be extended, x and y will be included. Obviously, the density function will become a joint density function and the integration will become a double integration. Similarly, the summation will become a two dimensional summation. So, this is the formula we will apply. So, a data is given that is related to x and y. X values are given, y values are given, and the corresponding probability combinations are given. X for different combinations of x, y, the corresponding probabilities are given. So, we are asked to compute the expectation of 2x plus 3y, expectation of x square minus y square, and the joint expectation of xy. So, firstly, to compute the expectation of 2x plus 3y. Expectation of 2x plus 3y means, we will apply the property of expectation. What we will get? 2 into expectation of x plus 3 into expectation of y. So, before computing this question, we need to know what is expectation of x, expectation of y. In a similar manner, expectation of x square minus y square. So, in the expectation of x square minus y square, if you expand, we will get expectation of x square minus expectation of y square. So, firstly we need to compute expectation of x square, expectation of y square. So, for that expectation of x formula, discrete version xi into p of xi, the combinations are given. See here the combination, x is equal to 1, probability is 1 by 2, 0, 1 by 3, minus 1, 1 by 6. So, minus 1 into 1 by 6, 0 into 1 by 3, 1 into 1 by 2. So, solving this, we will get expectation of x as 1 by 3. In a similar manner, expectation of y, different combinations are given at minus 1, 1 by 4, 0, 1 by 2, 1, 1 by 4. Applying that, minus 1 into 1 by 4, 0 into 1 by 2, 1 into 1 by 4, we will get 0. Next, expectation of x square, summation of xi square into p of xi. So, in place of x, I need to substitute xi square, 0 square, 1 square, 2 by 3, here minus 1 square, 0 square, 1 square, for y 1 by 2. So, we computed expectation of x square, expectation of y square, expectation of x, expectation of y. Here if you substitute 2 into 1 by 3, 2 into 1 by 3 plus 3 into 0. So, the expectation of 2x plus 3y, expectation of 2x plus 3y is 2 by 3. Similarly, expectation of x square minus y square, expectation of x square is 2 by 3, expectation of y square is 1 by 2. So, the difference we will get 1 by 6. And also we are asked to compute the joint expectation, which is also called as correlation Rxy, which is also called as sigma xy mu 1 1. So, now we need to compute the correlation. The formula for correlation is expectation of xy is equal to xi yj p of xi comma yj. So, substituting the joint probabilities, what we will get? The joint expectation or correlation is 0. That means there is no relationship between the random variables x and y. So, the joint moments, already we defined what is meant by joint moment, about the origin, joint moment about the mean. The definitions are given here. So, the joint moment is generally denoted with m and k. and the central moment is denoted with mu and k, and this is for continuous version. Similarly, for a discrete version it will be summation. In the joint moment about the origin, the important parameter which we are interested or focused is the correlation. Correlation Rxy is equal to expectation of xy is equal to rho xy. It gives you the measure of similarity between two random variables. Similarly, in the joint central moment, the important parameter which we focused is covariance. Covariance is also denoted as covariance co of x comma y cxy sigma xy, like this we can denote. There is a relationship between covariance and correlation. Covariance cxy is equal to rxy minus x bar into y bar. So, if you expand this relation, we will get this answer rxy minus x bar into y bar. Let us see few problems related to the joint moments. They are asking us to calculate g of xy is given xy whole square. So, the expectation of xy whole square means we need to substitute this function here xy whole square fxy of xy dx dy. The limits of x are defined over 0 to 6, the limits of y are defined over 0 to 4. Solving this integration, what we will get? 64. Now, we are asked to compute the covariance of two random variables. This is central moment. The second order central moment sigma xy is equal to covariance of xy, which is equal to rxy minus x bar into y bar, which is nothing but e of xy minus e of x into e of y. Given x is greater than 0, y is greater than 0, x plus y less than 1. So, x plus y less than 1 curve is something like this, 0 to 1, 0 to 1 are the maximum limits. So, the x limits and y limits are defined here. So, while doing the integration, we will fix one limit and we will use this relation for another limits. Let us say y is equal to 0 to 1, x is equal to 0 to 1 minus y maximum, fxy of xy dx dy. Fxy of xy is 2xy dx dy. So, first we will do the integration with respect to x. So, 2y is constant, bringing outside, doing the integration y into 1 minus y square. Again doing integration with respect to y and substituting the limits, we will get 1 by 12. The joint expectation is 1 by 12. Next, in order to compute the covariance, E of x and E of y are required. So, to compute the E of x, m10, that means in m n k, I need to replace k with 0, n is equal to 1. This is also called as first order moment, n plus k is equal to 1. Similarly, when n is equal to 0, k is equal to 1, again the order is 1, n plus k is equal to 1. Here, the case is m10 is E of x. Here the case is m01 is E of y. So, substituting E of x 1 by 3, E of y we will get 1 by 3. The covariance formula is E of xy minus E of x into E of y. 1 by 12 minus 1 by 9. We will get minus 1 by 36. Another problem which is related to the joint moments. Here they are asking us to compute all the possible third order moments. So, n comma k, n plus k is equal to 3. We need to identify the combinations. So, 3 plus 0, 0 plus 3, 2 plus 1, 1 plus 2. So, totally we need to compute 4 different moments, m30, m03, m21, m12. So, we will compute one by one third order moments. First m30, m30 means e of x cube into y power 0, y power 0 is 1 e of x cube into fxy of xy dx dy. X limits, y limits are substituted. Doing the integration and solving, what we will get the m30 as 0. Similarly, m03 means e of x power 0 y cube, e of y cube. Solving over the given limits, what we will get, finally substituting 0. Next m21, e of x square y 0. Similarly, m12, e of x y square this also 0. So, all the thoughts central moments for the given density function are 0. Next problem is to compute the second central moment. Second central moment is sigma 1 mu 1 1. Second central moment is mu 1 1, which is equal to sigma xy, which is equal to covariance of xy. Covariance of xy is equal to rxy minus x bar into y bar. In order to compute x bar, we need to know the marginal density function of x. So, to compute the marginal density function of the x, we need to do the integration with respect to y. We will get 2. Similarly, the marginal density function of y, to do the integration with respect to x, we will get 4e power minus 4y. Now, we need to compute the correlation, expectation of x, expectation of y, and finally, we need to substitute here. So, the correlation formula E of xy is xy into fxy of xy dx dy. E of x is x into fx of x dx. E of y is y into fy of y. So, totally we will get the covariance as 1 minus 1, 0. That means they are uncorrelated to each other. X and y are uncorrelated to each other. So, the covariance also describes the amount of relationship, linear relationship between two random variables x and y. So, here also they are asking us to compute the second central moment. The same thing we do. First, we need to compute marginal density function of x, marginal density function of y. E of xy you can compute directly since the data is being provided to us 1 by 3. The marginal density function of x is x plus 1 by 2. We will get the expectation of x as 7 by 12. Both are symmetrical. The marginal density function of y is y plus 1 by 2. The expectation is 7 by 12. So, substituting in the covariance formula, we will get the covariance as minus 1 by 144, which means x and y are not uncorrelated. There is some correlation between x and y. The amount of correlation is given by numerical value minus 1 by 144. Here they are asking us to calculate expectation of x plus y, expectation of x square plus y square, expectation of xy. Expectation of x means m10, expectation of y means m01, expectation of x square is m20, expectation of y square is m02, expectation of xy is m11. They are asking us to compute the first moments and all second order possible moments. So, based on the formula, after applying that expectation of x plus next expectation of x square plus y square, first we are computing expectation of x square symmetrically, expectation of y square, expectation of x square plus y square, we will get 1. So, expectation of xy is equal to expectation of x into expectation of y, which is equal to 1 by 4. So, the marginal density function of x is computed and substituted here, we will get 1 by 2. In a similar manner, expectation of y also, y into fy of y, y into 2 e power minus 2y, we will get 1 by 2. 1 by 2 into 1 by 2, 1 by 4. The condition is satisfied, they are 100% correlated. Next, they are asking us to compute the variance. Variance means second central moment. M20 represents variance of x, M02 represent variance of y. So, before computing the variance, we know the variance relation with respect to mean square value. This is mean square value minus mean whole square. So, before computing variance, I need to compute mean square value and mean value. Before doing that, we need to compute the marginal density function of x and y. Doing the integration with respect to y for the given limits, we will get 2 minus x minus 1 by 2. To get the marginal density function of y, doing the integration with respect to x, we will get 3 by 2 minus y. So, expectation of x square mean square value, expectation of x mean value, sigma x is already related in the previous slide. This is the variance we will get. In a similar manner, the variance of y also can be computed. The variance of y is equal to expectation of y square minus expectation of y whole square. So, in a similar manner, if you compute, you will get the same answer 11 by 144. we will get the same values. So in this session what we have seen is we have defined what is meant by joint moments. Already we have seen joint moments theoretical topics and the properties associated with joint moments. Here we have done a quick recap what is meant by joint moment, what is the mathematical formula for joint moment, and the important parameter in the joint moment. Joint moment about the origin gives you the correlation. Joint moment about the center or central value gives you the covariance. So we have seen the mathematical formulas of correlation and covariance, and also we solved so many problems which are related to joint moments, practical problems like computing first order moment, second order moment, third order moment, all the possible moments we calculated, and the important parameters like covariance, correlation we calculated. So in the next session what we will see is we will see the problems related to the random process. The concept is already we have seen. What is random process? We have defined random process, we have defined stationarity, all concepts. So we will solve more problems related to practical situation in the random process unit. Thank you.